what is hidden in the core of a neutron star. Right now, somewhere in this galaxy, there is an object no wider than the city of Manhattan that contains more mass than our entire sun. If you could somehow scoop out a single teaspoon of its material and bring it back to Earth, that tiny spoonful would weigh roughly 6 billion tons. That is heavier than every single car, truck, bus, and train on the planet combined. You could not hold it. The ground beneath it could not hold it. It would burn straight through the crust of the Earth like a white-hot ember dropped onto tissue paper. And that teaspoon came from the surface, the easy part, the place where the physics is still relatively well-behaved, because deeper inside, past a crust harder than anything else in the known universe, past layers of matter twisted into shapes that physicists have named after Italian food, there lies a core so dense, so extreme, so far beyond the reach of any laboratory experiment ever conducted, that no one on Earth can tell you with certainty what it is made of. To put the density in perspective, consider this. Water has a density of about 1 gram per cubic centimeter. Lead, one of the densest common materials on Earth, has a density of about 11 grams per cubic centimeter. The core of our sun, where hydrogen is being fused into helium at temperatures of 15 million degrees, has a density of about 150 grams per cubic centimeter. A white dwarf, the dead remnant of a sun-like star, reaches densities of about 1 million grams per cubic centimeter. But a neutron star core laughs at all of these numbers. Its density is roughly 100 trillion grams per cubic centimeter, or about 100 million times denser than a white dwarf and 1 trillion times denser than the core of our sun. At these densities, a sugar cube-sized chunk of neutron star material would outweigh Mount Everest. We know what the outside looks like. We know the broad strokes of the interior, but at the very center of a neutron star, in a space perhaps only a few miles across, matter exists in a state that may not occur anywhere else in the observable universe. It may be a sea of particles that have lost their individual identities, melted into a soup of their most fundamental building blocks. It may be a substance so exotic that it was last seen in the first microseconds after the Big Bang. It may be something that we have not yet imagined. This is one of the oldest open questions in modern physics, and despite decades of work by thousands of brilliant minds, it remains unsolved. So let us go there. Let us start at the violent birth of a neutron star in the death scream of a massive sun. And then let us descend, layer by layer, through a world more extreme than anything you have ever encountered, all the way down into the hidden heart of one of the universe's most mysterious objects. And to understand what might be hiding in that core, we first have to understand what dies to create it. The death of a giant stars are, at their most basic, a negotiation between two opposing forces. On one side is gravity, relentless and patient, always pulling inward, always trying to crush the star down to nothing. On the other side is the energy released by nuclear fusion, the process that converts lighter elements into heavier ones deep inside the star's core. That energy pushes outward, inflating the star like a balloon. And for most of a star's life, these two forces exist in a careful, dynamic balance. The star shines. It holds its shape. It endures, but all negotiations eventually end. A star like our sun will burn through its hydrogen fuel over the course of roughly 10 billion years, eventually swelling into a red giant before quietly shedding its outer layers and leaving behind a dense, cooling ember called a white dwarf. It is a dignified, if melancholy, end. But stars significantly more massive than our sun, stars 8 times heavier or more, do not go gently. They rage. And their rage creates something far stranger than a white dwarf. These massive stars burn through their fuel much faster than smaller stars, not because they have less of it, but because they burn it so much more ferociously. A star 20 times the mass of the sun might exhaust its hydrogen in only a few million years, a cosmic eye blink. And when the hydrogen at its core runs out, gravity does not simply win. The core contracts, temperatures climb, and a new round of fusion ignites, this time fusing helium into carbon. When the helium runs out, carbon fuses into neon, neon into oxygen, oxygen into silicon. Each successive fuel burns faster than the last, each one producing heavier elements, each one buying the star a little less time. If you could slice the star in half during this final stage, you would see something remarkable. A series of concentric shells, each burning a different element, layered like the rings of an onion. Hydrogen on the outside, then helium, then carbon, oxygen, silicon, and at the very center, a ball of iron about the size of the Earth. And this is where the story takes its dark turn. Because iron is the end of the line. Every element lighter than iron releases energy when it fuses. Every element heavier than iron absorbs energy when it fuses. Iron sits at the bottom of the nuclear binding energy curve, a thermodynamic dead end. The star has been living on borrowed time. And when that iron core reaches about 1.4 times the mass of our sun, a threshold known as the Chandrasekhar limit, the borrowing comes due all at once. In less than a second, the core collapses. The electrons, which until now have been providing a quantum mechanical pressure that helps hold the core up, are crushed into the protons by the unimaginable force of gravity. Each electron merges with a proton to form a neutron and a ghostly particle called a neutrino. In the space of a heartbeat, something like 10 to the power of 57 neutrinos, a number so large it has no intuitive meaning, flood outward from the collapsing core. These neutrinos carry with them a staggering amount of energy. Roughly 100 times more energy than our sun will produce over its entire 10 billion year lifetime. And they release it all in about 10 seconds. Meanwhile, the outer layers of the star are still falling inward. They slam into the newly formed core of neutrons, which has become so rigid, so incompressible, that it acts like a wall. The infalling material bounces off this wall with tremendous force, sending a shock wave screaming outward through the body of the star. This shock wave, energized by the flood of neutrinos, tears the star apart in one of the most violent events in the known universe, a supernova. The physics of this explosion, the precise mechanism by which the bounce of the core and the flood of neutrinos conspire to blow the star apart, remains one of the most computationally intensive problems in all of astrophysics. For decades, simple one-dimensional simulations could not get the explosion to work. The shock wave from the core bounce would stall, losing energy as it plowed through the still infalling outer layers, and the star would simply collapse into a black hole. It was only when physicists incorporated multidimensional effects, turbulent convection, standing accretion shock instabilities, and a more careful treatment of neutrino transport, that the simulations finally produced robust explosions. Even today, with some of the most powerful supercomputers on the planet dedicated to the problem, The details of core collapse supernova explosions are not fully resolved. We understand the broad strokes, but the devil lives in the turbulence, in the chaotic interplay of neutrinos and matter in those crucial seconds after the core bounce. What we do know is that the energy budget of such an explosion is staggering. The total gravitational binding energy released when the core collapses is about 3 times 10 to the 46 joules, a number so large that it has no parallel in everyday experience. Of this energy, roughly 99% is carried away by the neutrinos. Only about 1% goes into the kinetic energy of the explosion, the actual blowing apart of the star's outer layers, and only about 0.01%, 1/10,000th of the total, goes into the electromagnetic radiation that makes the supernova visible. Yet that tiny fraction is still enough to make the supernova spectacularly bright. The most famous nearby supernova in modern times was SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 160,000 light-years from Earth. First observed on February 23, 1987, it was the closest supernova visible to the naked eye since Kepler's supernova in 1604. About 2 hours before the light of the explosion reached Earth, 3 neutrino detectors around the world, Kamiokande in Japan, IMB in Ohio, and Baksan in Russia, detected a burst of neutrinos lasting only a few seconds. This was direct, experimental confirmation that core collapse supernovae produce the flood of neutrinos predicted by theory. It was also, in a poignant way, the first time humanity had detected a signal from the formation of a neutron star in real time. The light told us the star had died. The neutrinos told us what it had become. For decades after SN 1987A, astronomers searched for the neutron star they expected to find at the center of the expanding debris cloud. In 2024, NASA's James Webb Space Telescope finally found the best evidence yet for its presence, detecting infrared signatures of high-energy radiation from a probable young neutron star buried deep within the remnant. It had taken nearly 40 years, and one of the most powerful telescopes ever built to confirm what the neutrinos had whispered in 1987. For a few weeks, this single dying star can outshine an entire galaxy of 100 billion suns. The explosion flings the star's outer layers into space at speeds reaching tens of thousands of kilometers per second, enriching the surrounding cosmos with heavy elements: the carbon in your body, the oxygen you breathe, the iron in your blood. All of it was forged in the cores of massive stars and distributed across the galaxy by explosions exactly like this one. You are, in a very real and literal sense, made of dead stars. But what about that core? That ball of neutrons, incredibly hot, spinning furiously, compressed to a density that defies comprehension. It survives the explosion. It endures, and it will endure for billions upon billions of years, slowly cooling in the dark, a monument to the star that once was. This is a neutron star, and it is one of the most extraordinary objects in the entire universe, a city-sized sun. To appreciate just how extreme a neutron star is, you need to wrestle with some numbers that sound made up, but are not. A typical neutron star has a mass somewhere between 1.4 and 2.1 times the mass of our sun. The sun, for context, is so large that you could fit 1.3 million Earths inside it. Now take all of that mass, all of that unimaginable bulk and compress it into a sphere roughly 20 kilometers across. That is about 12 miles in diameter. That is smaller than many cities on Earth. You could drive across a neutron star in about 15 minutes. You could not, of course, actually do this, because you would be dead long before you arrived. But the mental image is useful. The density that results from this compression is almost impossible to convey in words that mean anything to the human brain. At the surface, the density is already extraordinary, something like 1 billion tons per cubic centimeter. But deeper inside, the density climbs even higher, reaching and then exceeding the density of an atomic nucleus, which is about 230 million tons per cubic centimeter. At the very center of the most massive neutron stars, the density may reach 5 to 10 times nuclear density, a regime where the behavior of matter becomes genuinely uncertain. The gravity at the surface of a neutron star is about 200 billion times stronger than gravity on the surface of the Earth. If you were somehow able to stand on a neutron star, which you absolutely cannot, you would be crushed into a film of atoms thinner than a sheet of paper in a fraction of a second. Any object falling onto the surface of a neutron star would hit at roughly 1/3 to 1/2 the speed of light. The impact energy of a single marshmallow hitting the surface at that speed would be comparable to a nuclear weapon. The surface itself is astonishingly smooth. The extreme gravity flattens any irregularities down to bumps no more than a few millimeters high. The tallest possible mountain on a neutron star, if you could even call it that, might be a centimeter or two. And yet even these tiny deformations matter, because they can produce ripples in the fabric of space-time itself, gravitational waves that, in theory, could be detected by instruments here on Earth. Then there is the rotation. When the original massive star collapsed, it was already spinning. But just like an ice skater pulling their arms in to spin faster, the conservation of angular momentum means that as the star shrinks from something the size of our sun down to something the size of a city, its rotation rate increases dramatically. Newly born neutron stars can spin many times per second. The fastest known neutron star, a pulsar designated PSR J17482446 AD, rotates 716 times every single second. Its surface at the equator is moving at roughly 1/4 the speed of light. And wrapping all of this is a magnetic field of staggering power. Earth's magnetic field is about 505 Tesla, roughly enough to deflect a compass needle. A typical neutron star's magnetic field is around 100 million to 1 trillion Tesla. The most magnetic neutron stars, called magnetars, have fields reaching up to 100 billion Tesla or more. A field that's strong would be lethal from 1,000 kilometers away. It would distort the electron clouds of your atoms, stretch them into thin cylinders aligned with the field, and rearrange the fundamental chemistry of your body before you even got close. At even greater field strengths, the vacuum of empty space itself begins to behave strangely, becoming birefringent, splitting light into two beams the way a crystal of calcite does on a tabletop. The surface temperature of a young neutron star is also extraordinary. Immediately after formation, the core reaches temperatures of around 100 billion degrees, far hotter than the center of any ordinary star. Within minutes to hours, neutrino emission cools the core down to about 1 billion degrees. Over the following million years or so, the temperature continues to drop, cooling through the emission of neutrinos from the interior and thermal photons from the surface. Even so, the neutron stars we can observe today, many of which are thousands to millions of years old, still have surface temperatures of around 1 to 2 million degrees, roughly 100 to 200 times hotter than the surface of the sun. This extreme heat means that neutron stars glow primarily in X-rays, a form of electromagnetic radiation far more energetic than visible light. It is for this reason that X-ray telescopes, mounted on satellites above Earth's X-ray absorbing atmosphere, have been among the most important tools for studying neutron stars. The Chandra X-ray Observatory, launched in 1999, and its European counterpart, Newton, launched the same year, have together provided thousands of observations of neutron stars in various stages of their lives, from newborn hot embers inside supernova remnants to ancient cold relics slowly fading into the cosmic background. Even the way neutron stars cool provides clues about their interiors. The rate at which a neutron star loses heat depends sensitively on the state of the matter inside it, because different forms of matter produce neutrinos at different rates, and neutrino emission is the primary cooling mechanism for the first million years or so. A neutron star with a core made of ordinary neutrons cools at one rate. A neutron star with a quark matter core cools at a different rate. A neutron star undergoing a superfluid phase transition cools differently still. By measuring the temperatures of neutron stars at different ages and comparing them to theoretical cooling curves, physicists can discriminate between competing models of the interior. This field, known as neutron star cooling theory, has been one of the most productive avenues for constraining the interior composition. And the discovery of the rapidly cooling Cassiopeia, a neutron star, in 2011, gave it a dramatic observational anchor point. These are the broad strokes of a neutron star. An object born in violence, compressed beyond comprehension, spinning with ferocious speed, wrapped in magnetic fields of almost absurd intensity. And yet for decades after they were first theorized, nobody knew for certain that they actually existed. That changed because of a graduate student, some scraps of paper, and a signal that was initially blamed on little green men. But before we get to that discovery, it is worth noting that neutron stars had been imagined long before they were observed. The story begins in 1932, the year James Chadwick discovered the neutron. Almost immediately, physicists began to wonder what would happen if you had enough neutrons packed tightly together. In 1934, just 2 years after Chadwick's discovery, Walter Baade and Fritz Zwicky, working at the Mount Wilson Observatory in California, published a remarkably prescient paper in which they proposed that supernovae could produce extremely compact objects composed almost entirely of neutrons. They called these hypothetical objects neutron stars and suggested that they would have radii of about 10 kilometers, a prediction that has proven remarkably accurate. In 1939, Robert Oppenheimer, the same physicist who would later lead the Manhattan Project, co-authored a paper with his student George Volkoff that derived the first mathematical models of neutron star structure using the equations of general relativity. The Tolman-Oppenheimer-Volkoff equation, as it came to be known, describes the balance between gravitational collapse and internal pressure inside a neutron star. Using this equation with a simplified model of non-interacting neutrons, Oppenheimer and Volkoff estimated a maximum neutron star mass of about 0.7 solar masses. This was too low, a consequence of their oversimplified equation of state. But the framework they established remains the foundation of neutron star physics today. More realistic calculations, incorporating the effects of nuclear forces between neutrons, predict maximum masses in the range of about 2.2 to 2.9 solar masses, broadly consistent with the most massive neutron stars observed. For 3 decades after Baud and Zwicky's prediction, neutron stars remained purely theoretical objects. They were too small and too dim to be detected with the telescopes of the era, and many physicists treated them as mathematical curiosities rather than real astrophysical objects. That skepticism evaporated in an instant in the late 1960s, thanks to an observation made by a young graduate student at Cambridge. A bit of scruff on the charts, the story of how humanity confirmed the existence of neutron stars, is one of the great tales in the history of science. And like many such tales, it begins with someone noticing something that everyone else had overlooked. The year was 1967. A young woman named Jocelyn Bell from Lurgan in Northern Ireland was working on her doctoral research at the University of Cambridge. Her supervisor, the radio astronomer Anthony Hewish, had designed a new radio telescope to study distant objects called quasars. And Bell had spent 2 years helping to build it, hammering posts into the ground and stringing wire across a field that covered 4.5 acres. The telescope produced prodigious amounts of data, over 100 meters of paper chart recordings every few days, and it was Bell's job to analyze every centimeter of it by hand. One day in the late summer of 1967, she noticed something peculiar. There was a signal on the charts that didn't look like any known source. It wasn't the steady glow of a distant galaxy or the flickering of a quasar. It was something else entirely. A tiny mark, occupying only about 2.5 centimeters of chart paper. Out of the roughly 120 meters she reviewed every 4 days. She described it later as a bit of scruff. Most people would have ignored it. Bell did not. Something about it stuck in her memory, and as she continued analyzing the data, her brain kept tugging at her, telling her she had seen something like this before from the same region of sky. She pulled out previous recordings and found the signal again, intermittent but recurrent, always appearing from the same patch of sky. By late November, using a faster recording device, she captured the signal in full detail. What she saw was extraordinary. The signal consisted of a string of radio pulses spaced exactly 1.337 seconds apart, keeping time with a precision that rivaled the best atomic clocks on Earth. Nothing in nature was known to produce signals this regular. The possibility that it might be artificial, a beacon from an intelligent civilization, was not lost on the team. They half-jokingly named the source LGM-1 for little green men. But Bell was not convinced it was aliens. She had been tracking the source for months and noted that it stayed fixed among the stars, rising and setting with them, behaving like a natural celestial object. And then she found a second pulsing source in a completely different part of the sky with similar properties. And then a third, and a fourth. The odds of multiple alien civilizations independently sending signals at Earth using identical technology from different directions seemed vanishingly small. The sources were natural. But what were they? The answer came quickly from the theoretical community. Thomas Gold and others identified the signals as coming from rapidly rotating neutron stars, objects that had been theorized decades earlier by Walter Baade and Fritz Zwicky in 1934, but never directly observed. These rotating stars had intense magnetic fields that channeled beams of radio waves from their magnetic poles. As the star spun, these beams swept across the sky like the beams of a lighthouse. If Earth happened to lie in the path of one of those beams, we would detect a regular pulse of radio emission with each rotation. The objects were named pulsars, a contraction of pulsating radio source, and the discovery was one of the most important in 20th century astronomy. It confirmed that neutron stars were real, that they rotated with extraordinary regularity, and that they could be observed and studied from across the galaxy. In 1974, the Nobel Prize in Physics was awarded for this discovery. But controversially, it went to Anthony Hewish and Martin Ryle rather than to Jocelyn Bell Burnell, who had made the actual observation. The omission sparked widespread criticism. Fred Hoyle, one of the most prominent astronomers of the 20th century, publicly objected. Bell Burnell herself responded with characteristic grace, stating that she felt it would have been inappropriate for the prize to go to a graduate student, but history has been kinder to her than the Nobel Committee was. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million. She donated the entire amount to fund scholarships for women, underrepresented minorities, and refugee students pursuing physics research. Her discovery opened a window into one of the most extreme environments in the universe, and through that window, physicists began to peer inward, trying to understand what these strange, dense, spinning objects were actually made of. Cosmic lighthouses and magnetic monsters, not all neutron stars, are created equal. The pulsars that Bell Burnell discovered were only one species in what turned out to be a surprisingly diverse family. As astronomers discovered more neutron stars over the following decades, they realized that these objects came in several distinct varieties, each with its own peculiarities, and each offering different clues about the physics of ultradense matter. The most common type, and the most well understood, is the rotation-powered pulsar. These are the descendants of Bell Burnell's original discovery, neutron stars that spin and emit beams of electromagnetic radiation powered by their rotational energy. As they radiate, they gradually slow down, converting rotational kinetic energy into electromagnetic waves. Most known pulsars fall into this category. They typically rotate anywhere from once every few seconds to once every few milliseconds, and their pulse timing is so precise that they can be used as natural clocks of extraordinary accuracy. Astronomers have used arrays of millisecond pulsars to search for gravitational waves rippling through the galaxy, a technique known as pulsar timing. And the results have provided some of the strongest indirect evidence for a universe filled with gravitational radiation. Millisecond pulsars are a special subclass, old neutron stars that have been spun up to incredible rotation rates by pulling in material from a companion star. As matter spirals down onto the neutron star's surface, it transfers angular momentum, accelerating the spin. The fastest of these, PSR J17482446 AD, completes 716 rotations every second. At that speed, a point on the star's equator is moving at roughly 70,000 kilometers per second, fast enough to travel from Earth to the Moon in about 5 seconds. But the most dramatic members of the neutron star family are the magnetars. These are neutron stars with magnetic fields so intense that they defy easy description. A typical neutron star has a magnetic field of around 100 million to a trillion Tesla. A magnetar's field is another 1,000 times stronger, reaching upward of 100 billion Tesla. For context, the strongest continuous magnetic field ever produced in a laboratory is about 45 Tesla. A magnetar's field is billions of times more powerful. These colossal fields have real, observable consequences. The crust of a magnetar, like any neutron star, is locked to its magnetic field. When the magnetic field shifts or restructures, the crust is forced to move with it. If the stress on the crust exceeds its breaking point, it fractures in what astronomers call a starquake. These fractures are the neutron star equivalent of earthquakes, except that the energy released is almost incomprehensibly greater. On December 27, 2004, a magnetar designated SGR 18-6-20, located roughly 50,000 light-years away in the constellation Sagittarius, produced a burst of gamma-ray energy so powerful that it briefly outshone every other source of gamma rays in the observable universe. In 1/10 of a second, this single neutron star released more energy than our sun will produce in 100,000 years. The burst was so intense that it measurably affected Earth's ionosphere. Despite the magnetar being halfway across the Milky Way, had the same event occurred within 10 light-years of Earth, it would have been catastrophic for life on our planet. The 2004 event from SGR 18-6-20 was not the first giant flare observed from a magnetar, but it was by far the most powerful. The initial spike of the flare lasted less than 1/4 of a second and reached a peak luminosity of about 10 to the 47 ergs per second, making it the brightest extrasolar event ever detected at gamma-ray energies at that time. The spike was followed by a softer, pulsating tail of X-ray emission that lasted several minutes, modulated by the magnetar's 7.56-second rotation period. The pulsations showed that the source of the emission was locked to the surface of the star, likely a fireball of trapped plasma confined by the magnetar's immense magnetic field. The sheer power of this event forced astrophysicists to rethink the energy budget of neutron stars. The energy released in a giant flare exceeds anything that can be produced by the rotational energy of the star or by ordinary nuclear processes. The only plausible power source is the magnetic field itself, which in a magnetar contains enough energy to produce such outbursts. The crust fracture model proposed by Thomson and Duncan, in which the magnetar's evolving magnetic field stresses the solid crust until it breaks, releasing a torrent of magnetic energy, remains the leading explanation for giant flares and the smaller, more frequent bursts that magnetars routinely produce. Magnetars are also prime suspects in one of modern astronomy's most tantalizing mysteries: fast radio bursts, or FRBs. These are intense, millisecond duration flashes of radio energy that arrive from distant galaxies. First detected in 2007, they were initially baffling, but evidence has been accumulating that at least some of them originate from magnetars. In 2020, a magnetar within our own galaxy, SGR 1935 + 2154, produced a burst that was simultaneously detected in both radio waves and X-rays, providing the strongest evidence yet for the connection between magnetars and fast radio bursts. The existence of magnetars was first proposed in 1992 by Robert Duncan and Christopher Thompson, who showed that under certain conditions during a neutron star's formation, a dynamo mechanism could amplify the magnetic field to truly monstrous levels. It is estimated that perhaps 1 in every 10 neutron stars is born as a magnetar. Their active phase is short by cosmic standards, lasting only about 10,000 years before their magnetic fields decay enough for the extreme activity to cease. After that, the former magnetar continues to exist as a more ordinary, if still incredibly dense, neutron star, quietly cooling in the dark. There is one more observational frontier worth mentioning before we descend beneath the surface, and it concerns a property of neutron stars that may seem surprising: their shape. A perfectly spherical, perfectly fluid neutron star would be unremarkable from a gravitational wave perspective. But real neutron stars are not perfectly spherical. Their solid crusts can sustain tiny deformations, bumps or mountains created by the star's magnetic field, by residual stresses from its formation, or by the accumulated weight of accreted material. These mountains are laughably small by terrestrial standards, perhaps a fraction of a millimeter high on a star 10 kilometers across. But because the neutron star is spinning, any asymmetry in its mass distribution produces a time-varying gravitational field. That time-varying field radiates gravitational waves continuously, not in a dramatic burst like a merger event, but in a faint, steady hum at twice the star's rotation frequency. Detecting this continuous gravitational wave signal is one of the holy grails of gravitational wave astronomy. It would provide a direct measurement of the size of the mountain, which in turn would constrain the breaking strain of the neutron star crust, telling us how strong the nuclear material is, and indirectly informing us about the composition and structure of the crust layers. So far, no continuous gravitational wave signal has been detected from any neutron star, despite extensive searches by LIGO and Virgo. This non-detection already places upper limits on the size of neutron star mountains, limits that are consistent with, but do not yet definitively test, theoretical predictions for the maximum mountain size supportable by a nuclear crystal lattice. Future detectors with greater sensitivity may finally catch this whisper of deformed spinning matter, adding yet another tool to the arsenal for probing neutron star interiors. Beyond pulsars and magnetars, there is another class of neutron star that has proven invaluable for understanding their interiors: X-ray binaries. These are systems in which a neutron star orbits close to a companion star, typically a normal main sequence star or a bloated red giant. If the companion is close enough or large enough, its outer layers spill over toward the neutron star, drawn by the immense gravitational pull. This material does not fall directly onto the surface. Instead, because it carries angular momentum from the companion's orbit, it spirals inward, forming a swirling accretion disk of superheated gas around the neutron star. Friction within this disk heats the gas to millions of degrees, causing it to glow brightly in X-rays. The accretion process can also trigger one of the most violent phenomena associated with neutron stars: thermonuclear X-ray bursts. As hydrogen and helium from the companion accumulate on the neutron star's surface. They are compressed and heated by the star's extreme gravity. Eventually, the temperature and pressure at the base of this accumulated layer reach a threshold where thermonuclear fusion ignites. Not the steady, controlled fusion that powers ordinary stars, but a runaway explosion that engulfs the entire surface of the neutron star in a matter of seconds. The resulting burst of X-rays can briefly outshine the rest of the accretion disk by a factor of 10 or more, and then fade over the following 10 to 100 seconds as the nuclear fuel is consumed and the surface cools. These bursts are more than just spectacular light shows. They are probes of the neutron star surface. The way the burst rises and fades, the peak temperature it reaches, the presence or absence of spectral lines in the emitted X-rays, all of these carry information about the composition and structure of the outermost layers of the star. Some bursts, called photospheric radius expansion bursts, are so powerful that the radiation pressure temporarily lifts the outer layers of the atmosphere off the surface, causing the apparent radius to expand before the material falls back. These special bursts can be used to estimate the neutron star's mass and radius. Because the luminosity at which the atmosphere lifts off, the Eddington luminosity, depends on the star's surface gravity. In rare cases, the accumulated fuel undergoes a particularly energetic type of burning that involves carbon fusion deep within the accumulated layers. These events, called superbursts, last for hours instead of seconds and release 1,000 times more energy than a typical Type 1 burst. They are thought to ignite at depths of about 10 meters below the surface, in the ocean layer, and their properties are sensitive to the thermal conductivity and composition of the crust beneath. In this way, even a brief flash of X-ray light from a distant neutron star carries, encoded within it, clues about the physics operating kilometers beneath the surface. Hundreds of X-ray burst sources have been cataloged since the first ones were detected in the 1970s by the Uhuru and Vela satellites. Together with pulsars, magnetars, and isolated cooling neutron stars, they form a complementary set of observational windows into the physics of ultradense matter, each one illuminating a different aspect of the puzzle. But whether a neutron star is a pulsar, a magnetar, an X-ray burster, or something in between, its external behavior is ultimately determined by what lies within. And what lies within is a world of almost surreal strangeness. Peeling back the layers, imagine, if you can, that you have been given the power to shrink yourself down and descend through the body of a neutron star, starting at its surface and traveling inward toward its center. What would you encounter? The outermost layer is the atmosphere, and it is almost negligibly thin, just a few centimeters to perhaps a meter in depth. Despite its thinness, it plays an outsized role in how we observe neutron stars, because it is the atmosphere that produces the thermal radiation we detect with X-ray telescopes. The composition of this atmosphere is uncertain and probably varies from star to star. Some neutron stars may have hydrogen or helium atmospheres accreted from surrounding material. Others, particularly those that have never interacted with a companion star, may have atmospheres of heavier elements, perhaps carbon or even iron. The exact composition matters enormously for interpreting observations, because different atmospheric compositions produce different spectral signatures, and misidentifying the atmosphere can lead to significant errors in estimating the star's temperature and radius. beneath the atmosphere lies what some astrophysicists poetically call the ocean, a liquid layer of ions and electrons, perhaps a few meters to a few tens of meters deep. The ions here are heavy nuclei, the familiar elements of the periodic table, arranged not in a crystalline solid, but in a hot, dense, electrically conducting liquid. The dynamics of this ocean are governed by the neutron star's rotation and its magnetic field, and they can give rise to complex fluid flows and magnetic instabilities. This ocean, thin as it is, has a surprisingly rich physics. The liquid is so dense, roughly 1 million grams per cubic centimeter near its base, that the ions in it are strongly coupled, meaning the electrostatic energy between neighboring ions greatly exceeds their thermal energy. The result is a liquid that behaves more like a viscous syrup than water, with the ions arranged in a short-range order that approaches, but does not quite reach, the regularity of a crystal. Whether the ocean freezes into a solid crust at its base or transitions smoothly depends sensitively on the temperature and composition, factors that are different for every neutron star and that evolve as the star ages and cools. The ocean is also where some of the most dramatic observable events on a neutron star's surface originate. When material from a companion star rains down onto the neutron star during accretion, it accumulates first in the ocean. As the pressure and temperature at the ocean's base increase, the accreted hydrogen and helium undergo thermonuclear burning, producing the type 1 X-ray bursts that have been observed from hundreds of neutron star systems. The ignition conditions, the burning speed, and the way the flame propagates across the surface all depend on the properties of the ocean. Its thermal conductivity, its viscosity, its composition, and how effectively it mixes the freshly accreted fuel. Some of the most sophisticated computational simulations in nuclear astrophysics are devoted to modeling these ocean dynamics, treating the thin liquid layer as a kind of nuclear furnace, whose behavior is governed by the interplay of gravity, rotation, and thermonuclear reactions. Below the ocean, things get more interesting. You enter the outer crust, a region that extends down perhaps a kilometer or so beneath the surface. Here, the material is solid, or more accurately, it forms a crystalline lattice, similar in principle to the crystal structure of metals on Earth, but under vastly different conditions. The nuclei in this lattice are primarily iron, or iron group elements, surrounded by a sea of degenerate electrons that provide most of the pressure holding the lattice up against gravity. As you descend deeper into the outer crust, the pressure and density increase relentlessly, and the nuclei in the lattice begin to change. They become increasingly neutron-rich, bloated with extra neutrons that are forced into them by the crushing pressure. These neutron-rich nuclei are unstable by the standards of ordinary physics. If you could somehow extract one and bring it to the surface of the Earth, it would fly apart in a tiny fraction of a second. But within the neutron star, the extreme pressure holds them together, freezing them in configurations that exist nowhere else in the natural universe. Then, at a density of about 4 times 10 to the 11th grams per cubic centimeter, something remarkable happens. The nuclei become so bloated with neutrons that they can no longer contain them all. Neutrons begin to leak out, dripping free from the nuclei and forming a gas of free neutrons that pervades the spaces between the lattice nuclei. This point is known as the neutron drip line, and it marks the boundary between the outer crust and the inner crust. The neutron drip is one of those transitions in physics that sounds mundane when described in words, but is actually quite dramatic when you think about what is happening. In ordinary matter, neutrons are securely bound inside atomic nuclei, held there by the strong nuclear force. The energy required to remove a neutron from a stable nucleus, like iron-56, is about 8 million electron volts, which is enormous by atomic standards. But inside a neutron star's outer crust, the extreme density and the resulting electron capture reactions have produced nuclei so far from the valley of stability that their neutron binding energy drops to zero. The nuclei are saturated with neutrons, like a sponge that can hold no more water, and the excess neutrons simply spill out. Below the neutron drip line, the material is a two-component system, solid nuclear lattice on one hand, and a gas, or liquid, of free neutrons on the other. The free neutron gas contributes to the pressure that supports the crust against gravity, and its properties, particularly its superfluidity, have profound effects on the observable behavior of the neutron star. In particular, the interaction between the superfluid neutrons and the solid crust is thought to be responsible for pulsar glitches, those sudden speed-ups in rotation that provide some of our most direct evidence for superfluid behavior inside neutron stars. The inner crust is where the strangeness truly begins. Here, the nuclei are enormous by the standards of normal matter, containing hundreds of nucleons apiece. They sit in a lattice, just as in the outer crust, but now they are immersed in a flowing sea of free neutrons. These free neutrons are believed to be in a superfluid state, meaning they flow with absolutely zero viscosity, zero friction. On Earth, achieving superfluidity requires cooling matter to within a fraction of a degree above absolute zero. Inside a neutron star, the same phenomenon occurs at temperatures of hundreds of millions of degrees, a consequence of the extraordinary densities and the quantum mechanical behavior of matter under these conditions. The inner crust extends down about another kilometer, and as you push deeper, the density continues to climb. The nuclei grow larger and larger, and the sea of free neutrons grows thicker and thicker until the nuclei begin to lose their distinct shape. They are no longer neat, round objects. They are being deformed, stretched, and crushed into exotic configurations by the competing forces of nuclear attraction and electrical repulsion. And it is here, in this twilight zone between the crust and the core, that you encounter one of the most strangely beautiful phenomena in all of physics. Physicists call it nuclear pasta, and it is exactly as whimsical as it sounds. The strongest material in the universe, at the base of a neutron, star's inner crust, in a region sometimes called the mantle. Something extraordinary happens to the building blocks of matter. The nuclei, which have been growing progressively larger and more neutron-rich as you descend, reach a point where they can no longer maintain their familiar spherical shapes. The competition between two fundamental forces, the nuclear strong force pulling nucleons together and the electromagnetic force pushing protons apart, produces a stalemate. And in that stalemate, matter arranges itself into structures unlike anything found anywhere else in the cosmos. The idea that such structures might exist was first proposed in the 1980s by Dennis Ravenhall, Christopher Pethick, and Douglas Wilson, who realized that the interplay between nuclear attraction and Coulomb repulsion at the densities found in neutron star crusts would inevitably produce non-spherical nuclear configurations. Their calculations showed that as the density increased, nuclei would be progressively deformed from spheres into cylinders, then into sheets, then into inverse geometries, a sequence of phase transitions driven by the changing balance of forces. When other physicists noticed that these shapes resembled various types of Italian cuisine, the names stuck, and nuclear pasta entered the lexicon of astrophysics. It is one of those cases where the naming convention in physics manages to be simultaneously absurd and perfectly descriptive. The simplest of these structures are semi-spherical blobs of nuclear material, oversized nuclei containing tens or even hundreds of nucleons apiece, sitting in a sea of free neutrons and electrons. Physicists, who evidently enjoy their dinners, have named this the gnocchi phase, after the small Italian dumplings. As you descend deeper and the pressure increases, these gnocchi get squeezed together. The electrical repulsion between their protons is no longer sufficient to keep them separate, and they fuse into long, rod-like cylinders of nuclear matter. This is the spaghetti phase. Deeper still, the spaghetti rods are compressed further and merge into flat, parallel sheets of nuclear material, separated by gaps filled with neutron gas. This is the lasagna phase. Continuing downward, the geometry inverts. Instead of sheets of nuclear matter separated by gaps, you now have a continuous mass of nuclear material, punctured by cylindrical tunnels filled with neutron gas. This is sometimes called the Bucatini phase, or the anti-spaghetti phase, named after the hollow tubular pasta. And finally, at the greatest depths before the core proper begins, those tunnels shrink into scattered spherical voids, bubbles of neutron gas within an otherwise uniform nuclear medium. This is the Swiss cheese phase, although some researchers have suggested calling it the anti-gnocchi phase to maintain the Italian culinary theme. The names are playful, but the physics is deadly serious. Nuclear pasta, if it exists, would be the strongest material in the known universe. In 2018, a team led by Matt Kaplan at McGill University ran the largest computer simulations ever conducted of neutron star crust material. They virtually stretched and compressed the nuclear pasta to determine its breaking point, and found that it is roughly 10 billion times stronger than steel. It dwarfs the strength of graphene and carbon nanotubes, materials that are themselves considered extraordinary on Earth. The reason for this incredible strength is straightforward. The nuclear strong force is the most powerful of all the fundamental forces of nature at short range. And in nuclear pasta, that force is operating in geometric configurations that maximize its structural integrity. The existence of nuclear pasta has not been directly observed, which is unsurprising given that we cannot exactly take a core sample from a neutron star. But there is tantalizing, indirect evidence. In 2013, a team led by José Pons at the University of Alicante in Spain found that the presence of nuclear pasta in the inner crust could explain a previously puzzling observation about pulsar spin rates. Astronomers had noticed that no pulsar had ever been observed with a spin period longer than about 12 seconds, which was strange because theory predicted that pulsars should be able to slow down to much longer periods. Pons and his colleagues showed that if nuclear pasta existed, its high electrical resistivity would cause the neutron star's magnetic field to decay faster than expected. A weaker magnetic field would be less effective at radiating electromagnetic energy, which would prevent the pulsar from slowing down beyond a certain point. The observations matched the predictions neatly. More recent work has explored how nuclear pasta might affect other observable properties of neutron stars. The pasta layer, though only about 100 meters thick, contains a significant fraction of the crust's total mass, roughly 1% of a solar mass, which is still an enormous amount of material. Its thermal and electrical conductivity, its viscosity, and its response to the magnetic field all influence how the neutron star cools, how it conducts heat, and how its magnetic field evolves over time. Understanding nuclear pasta is therefore not just a matter of satisfying curiosity about an exotic state of matter. It is directly relevant to interpreting astronomical observations and building accurate models of neutron star behavior. And yet nuclear pasta, strange as it is merely the appetizer. Because once you pass through the pasta layer and enter the core of the neutron star, you leave behind the world of atomic nuclei entirely and enter a domain where the rules of physics, as we know them, reach their breaking point. The superfluid heart, the transition from the inner crust to the outer core of a neutron star, is not a sharp boundary like the surface of the Earth. It is more of a gradual dissolving. The nuclear pasta structures, those exotic sheets and rods and bubbles, become increasingly uniform as you descend, until at some critical density, roughly the density of a single atomic nucleus, the distinction between nuclei and gaps vanishes entirely. You have entered the outer core, a region that makes up the vast bulk of the neutron star's volume, and that extends from roughly a kilometer below the surface down to within a few kilometers of the center. In the outer core, matter exists as a uniform, liquid mixture of neutrons, protons, and electrons, with a small admixture of particles called muons, which are heavier cousins of the electron. The neutrons outnumber everything else by a wide margin, typically making up about 95% of the matter by number. The remaining 5% is a mix of protons and leptons, electrons and muons. Their relative abundances determined by the requirement that the material be in beta equilibrium, meaning that the rate of neutrons decaying into protons and electrons is exactly balanced by the rate of protons capturing electrons to become neutrons. This liquid is unlike any liquid you have ever encountered. For one thing, the neutrons in it are believed to be superfluid. Superfluidity, as a phenomenon, was first discovered on Earth in the 1930s, when physicists cooled liquid helium to temperatures below about 2.2 Kelvin, just a couple of degrees above absolute zero. Below that temperature, helium atoms pair up in a quantum mechanical arrangement called Cooper pairs, named after Leon Cooper, one of the three physicists who explained the phenomenon and shared the 1972 Nobel Prize in Physics for the work. These Cooper pairs behave collectively as a single quantum entity, flowing without any friction or viscosity whatsoever. Superfluid helium can do seemingly impossible things. It can climb up the walls of a container and flow over the rim. It can pass through microscopic cracks that would stop any normal fluid. And it forms quantized vortices rather than ordinary turbulence when stirred. In a neutron star, the same basic physics applies, but under wildly different conditions. Instead of helium atoms at a few degrees above absolute zero, the Cooper pairs are formed by neutrons at temperatures of hundreds of millions of degrees. The idea that this might happen was first proposed by Arkady Migdal in 1959. Just 2 years after the BCS theory of superconductivity was published, Migdal realized that the same mechanism that causes electrons to pair up in superconductors could cause neutrons to pair up inside a neutron star, creating a superfluid state at temperatures that would seem impossibly hot by terrestrial standards. The first direct evidence for neutron star superfluidity came in 2011 from observations of the neutron star at the heart of the Cassiopeia, a supernova remnant, often called Cas A. This neutron star, located about 11,000 light-years from Earth, is one of the youngest known, born in a supernova explosion that would have been visible from Earth about 330 years ago using NASA's Chandra X-ray Observatory. 2 independent research teams discovered that Cas A's neutron star was cooling far more rapidly than standard models predicted. Between 2000 and 2009, its temperature had dropped by about 4%, from roughly 2.12 million Kelvin to 2.04 million Kelvin. Both teams reached the same conclusion. The rapid cooling could be explained if neutrons inside the star were in the process of forming Cooper pairs and transitioning into a superfluid state. When neutrons pair up, they release energy in the form of neutrinos, particles that stream freely out of the star and carry heat away with them. This Cooper pair formation creates a brief but significant burst of enhanced cooling. The teams calculated that the transition had begun within the last century or so as observed from Earth, meaning we were watching it happen in something close to real time. The protons in the outer core, meanwhile, are believed to be in a superconducting state. Since protons carry an electric charge, their Cooper pairs form a superconductor rather than a superfluid, meaning that electric currents can flow through the proton component without any resistance at all. This has profound implications for the neutron star's magnetic field. In a normal conductor, a magnetic field would gradually dissipate as the currents sustaining it lost energy to electrical resistance. In a superconductor, those currents can persist indefinitely, and the magnetic field becomes frozen into the material. This is part of the reason why neutron stars can maintain such extraordinarily strong magnetic fields for millions of years. The interplay between the neutron superfluid and the proton superconductor gives rise to some of the most exotic physics in the outer core. The neutron superfluid, when the star rotates, forms an array of tiny, quantized vortices, each one carrying a specific unit of angular momentum. The density of these vortices is staggering. A typical neutron star might contain roughly a billion vortex lines threading through its interior. Similarly, the proton superconductor, threaded by the star's magnetic field, forms an array of magnetic flux tubes. The interactions between these vortex lines and flux tubes govern how the star's rotation couples to its magnetic field and vice versa. These interactions are also thought to be responsible for one of the most dramatic observable phenomena associated with neutron stars: glitches. A pulsar glitch is a sudden, tiny increase in the rotation rate of a pulsar, followed by a gradual relaxation back toward its original speed. The largest glitches involve changes in rotation rate of only a few parts in a million. But given the enormous angular momentum of a neutron star, even this tiny fractional change represents a significant transfer of energy. The leading explanation is that glitches occur when the superfluid vortices in the inner crust, or outer core, which are normally pinned to the solid crust by nuclear forces, suddenly unpin and redistribute themselves. This transfers angular momentum from the faster spinning superfluid to the slower spinning crust, producing the observed speed-up. The most prolific glitcher among known pulsars is the Vela pulsar, located about 900 light-years from Earth in the constellation Vela. Since its discovery in 1968, the Vela pulsar has experienced more than 20 large glitches, roughly one every 3 years. Each glitch provides a window into the superfluid interior. Because the size of the glitch and the timescale of the subsequent relaxation depend on the properties of the superfluid, the strength of its coupling to the crust, and the density of vortex lines. By studying these glitches across many pulsars, physicists have been able to estimate that the superfluid in the inner crust contains roughly 1 to 2% of the total moment of inertia of the star, a measurement that provides direct, quantitative information about the distribution of matter inside the neutron star. Even more impressively, recent studies have shown that the pattern of glitch recovery, the slow relaxation that follows the initial speed-up, contains information about the temperature and viscosity of the superfluid. Different theoretical models of the interior predict different recovery timescales. And by fitting the observed recovery curves to these models, researchers can discriminate between competing pictures of the neutron star's internal structure. It is a remarkable chain of inference. Observing the arrival times of radio pulses from a spinning dead star thousands of light years away, and from those arrival times deducing the properties of a quantum mechanical fluid flowing without friction deep beneath its surface. In 2013, astronomers discovered something even more unexpected than a glitch: an anti-glitch. The magnetar 1E2259 plus 586, monitored by NASA's SWIFT satellite, was observed to suddenly slow down rather than speed up. This was the opposite of every glitch that had been observed before, and it required an entirely different mechanism to explain. One possibility is that the superfluid vortices in this magnetar, instead of unpinning and transferring angular momentum outward to speed up the crust, somehow transferred angular momentum inward, or that a sudden rearrangement of the magnetic field braked the crust directly. The anti-glitch remains poorly understood, but its very existence demonstrates that the interplay between the superfluid interior and the solid crust is far richer and more complex than the simplest models suggest. The superfluid state of the outer core also profoundly influences how heat moves through the neutron star. In a normal fluid, heat is transported by convection, the physical movement of hot material from one place to another. In a superfluid, however, heat transport works differently. Because the superfluid component flows without viscosity, it can carry enormous amounts of heat with extraordinary efficiency. The mechanism is related to what physicists call the two-fluid model, in which the superfluid is treated as a mixture of two interpenetrating components. A superfluid component that carries no entropy, and a normal component that carries all the entropy. Heat in this picture is transported by the flow of the normal component relative to the superfluid component, a process that can be astonishingly fast. In liquid helium on Earth, this mechanism, called second sound, allows heat to propagate as a wave rather than diffusing slowly as it does in ordinary materials. Inside a neutron star, An analogous process may allow heat from the deep interior to reach the surface far more quickly than it would in a non-superfluid star, directly affecting the observed cooling rate and surface temperature. The outer core, with its superfluid neutrons and superconducting protons, is already a place where matter behaves in ways that have no parallel on Earth. But it is not the most extreme part of the neutron star. That distinction belongs to the inner core, a region where the density reaches such extraordinary values that even the concept of a neutron may lose its meaning. Where physics breaks down the inner core of a neutron star is the most uncertain, most debated, and most fascinating region of these objects. It exists only in the most massive neutron stars, those with masses significantly above the typical 1.4 solar masses, and it occupies the central few kilometers of the star. Here, the density exceeds 2 to 3 times the density of ordinary nuclear matter, and may reach 5 to 10 times that value at the very center. And this is where the trouble begins for physicists, because at these densities, we simply do not know what matter does. The fundamental challenge is that the physics governing matter at nuclear density and above is described by quantum chromodynamics, or QCD, the theory of the strong nuclear force. QCD is a beautiful and elegant theory, one of the pillars of the standard model of particle physics, and it has been spectacularly successful at explaining the behavior of quarks and gluons at high energies. But it has a crippling weakness. It is almost impossible to calculate with at the densities and temperatures found inside neutron star cores. To appreciate why, consider how QCD differs from the other fundamental theories of physics. Electromagnetism, which governs the interactions of charged particles through the exchange of photons, is a weak enough force that calculations can be done using perturbation theory, a mathematical technique that involves computing a series of increasingly small corrections to a simple starting point. At each step, the corrections get smaller, and the sum converges to an accurate answer. Gravity, at least in the weak field regime relevant to most of the universe, can be treated similarly using Newtonian mechanics or the post-Newtonian approximations of general relativity. QCD, however, is different. At high energies, corresponding to quarks moving very fast or being very close together, the strong force actually becomes weaker. This property, discovered in the 1970s by David Gross, Frank Wilczek, and David Politzer, who shared the 2004 Nobel Prize for the work, is called asymptotic freedom. It means that at sufficiently high energies, quarks interact weakly enough that perturbation theory works, and calculations can be done reliably. This is the regime probed by particle colliders, and it is why QCD has been so successful at explaining the results of high-energy scattering experiments. But at lower energies, corresponding to the conditions inside ordinary matter or inside neutron star cores, the strong force becomes strong, really strong. So strong that perturbation theory breaks down completely. The corrections at each step of the calculation are not smaller than the previous ones. They are larger. The mathematical series diverges instead of converging, and the entire perturbative framework collapses. This is the regime of confinement, where quarks are bound inside hadrons, and it is the regime that governs neutron star interiors. There is a computational technique called lattice QCD that can in principle handle this non-perturbative regime. Lattice QCD discretizes spacetime onto a four-dimensional grid and uses massive computer simulations to numerically evaluate the behavior of quarks and gluons. It has been enormously successful at calculating properties of hadrons and the high-temperature quark-gluon plasma. But at finite baryon density, the regime relevant to neutron stars, lattice QCD runs into a technical obstacle called the sign problem. The mathematical quantities that need to be summed oscillate wildly, with positive and negative terms of nearly equal magnitude, making the computation intractably noisy. Despite decades of effort, the sign problem remains unsolved, and lattice QCD cannot yet directly simulate the conditions inside neutron star cores. This is why the interior of a neutron star is sometimes called the last frontier of QCD. It lies in a region of the phase diagram of matter, the abstract space that maps out all possible states of QCD matter as a function of temperature and density that cannot be reached by any existing computational or experimental technique. We can access high temperature and low density at particle colliders. We can access zero temperature and zero density in the vacuum. We can access moderate densities in nuclear physics experiments, but the cold, dense matter inside a neutron star occupies a blank spot on the map, a region where our theoretical tools give way, and we must rely on indirect evidence to guide us. The reason is a property of QCD called confinement. In everyday matter, quarks are always found bound together inside larger particles called hadrons, the most familiar of which are protons and neutrons. Each proton contains 2 up quarks and 1 down quark. Each neutron 2 down quarks and 1 up quark. And these quarks are bound together by gluons, the carrier particles of the strong force. The force between quarks has a peculiar property. It does not weaken with distance, the way gravity or electromagnetism does. Instead, it remains roughly constant or even increases as quarks are pulled apart. Trying to pull a quark out of a proton is like trying to stretch a rubber band that never breaks. The energy you invest eventually becomes so large that it spontaneously creates new quarks, which immediately bind with the original ones to form new hadrons. You never get a free quark. This confinement means that at ordinary densities, quarks are locked inside their parent particles, and matter is described in terms of hadrons, primarily neutrons and protons. But at the extreme densities inside a neutron star's inner core, the hadrons are squeezed so close together that they overlap. The quarks inside neighboring neutrons are no longer separated by meaningful distances. They are jammed up against each other, their identities blurring. At this point, several things might happen, and which one actually occurs is the central question of neutron star interior physics. The simplest possibility is that nothing exotic happens at all. The core might simply consist of neutrons, protons, electrons, and muons, the same particles found in the outer core, just packed more tightly together. The interactions between these particles would be described by increasingly complex and difficult to calculate nuclear forces. But the fundamental nature of the matter would remain hadronic. This is sometimes called the nucleonic model. And while it is the most conservative hypothesis, it is also the hardest to reconcile with some observations. Measurements from NASA's NICER instrument aboard the International Space Station, which has precisely determined the masses and radii of several neutron stars, suggest that simple nucleonic models may not be stiff enough to support the most massive observed neutron stars. Something more complex may be required. It is worth pausing here to explain what physicists mean by stiff and soft equations of state, because these terms come up constantly in discussions of neutron star interiors. The equation of state is a mathematical relationship between the pressure and density of a material. A stiff equation of state is one in which the pressure increases rapidly with density. This means the matter pushes back strongly against compression, which produces a larger, more resistant neutron star for a given mass. A soft equation of state, by contrast, is one in which the pressure increases more slowly with density. The matter is more compressible, and the resulting neutron star is smaller and more compact. The existence of neutron stars as massive as 2 solar masses places a strong lower bound on the stiffness of the equation of state. Whatever matter is doing inside the core, it must be generating enough pressure to hold up against the crushing weight of 2 suns. This is a surprisingly stringent requirement, and it has ruled out many theoretical models that predict 2 soft equations of state. The theoretical maximum mass a neutron star can have before it inevitably collapses into a black hole is called the Tolman-Oppenheimer-Volkoff limit, or TOV limit, named after the same Oppenheimer who first showed that massive stars could collapse beyond recovery. The exact value of this limit is unknown because it depends on the equation of state, but most current models place it somewhere between 2.2 and 2.9 solar masses. Below this limit, the internal pressure of the neutron star material, whatever that material may be, is sufficient to resist gravity. Above it, no known force can prevent collapse. The existence of this limit creates a fascinating puzzle when combined with observations. Gravitational wave detections have revealed a so-called mass gap, a range of masses between about 2.5 and 5 solar masses, where very few compact objects have been found. Below this gap sit the neutron stars. Above it sit the black holes. The gap, if it is real and not just an artifact of observational bias, might be telling us something profound about how massive stars die and what determines whether their remnants become neutron stars or black holes. It might also be telling us about the equation of state itself, because the upper edge of the neutron star mass distribution is, by definition, the TOV limit. Pinning down this edge with observations would immediately constrain the equation of state at the highest densities achievable in any neutron star, the very densities where exotic matter is most likely to appear. This is why every new mass measurement of a heavy neutron star is treated as a major event in the astrophysics community. The discovery of PSR J300 and 48 plus 400 and 32 at 2.01 solar masses in 2013, and PSR J700 and 40 plus 6620 at about 2.08 solar masses in 2019, and the even heavier PSR J900 and 52-607 at an estimated 2.35 solar masses in 2022. Each one pushed the lower bound on the TOV limit higher and tightened the screws on theoretical models. Each one demanded that the equation of state be stiff enough to support these weights, eliminating entire families of models that predicted too early collapse. A second possibility involves hyperons. Hyperons are particles similar to protons and neutrons, but containing one or more strange quarks in addition to the usual up and down quarks. On Earth, hyperons are produced in particle accelerators and decay almost instantly, within about a 10 billionth of a second, but inside a neutron star core, where the Fermi energy of the neutrons is high enough, it becomes energetically favorable to convert some neutrons into hyperons. The problem is that hyperons are generally softer than neutrons, meaning they provide less pressure at a given density. Including hyperons in neutron star models tends to make the maximum mass too low to match observations. This is known as the hyperon puzzle, and resolving it is an active area of research. A third possibility involves the formation of Bose-Einstein condensates of mesons, specifically pions or kaons, which are quark-antiquark pairs. Under certain conditions of density and temperature, these particles might condense into a quantum state where a large fraction of them occupy the lowest energy level. Similar to how atoms in a Bose-Einstein condensate behave in laboratory experiments, but under vastly more extreme conditions. Such condensates would significantly alter the equation of state and could affect how the star cools and evolves. But perhaps the most dramatic and widely discussed possibility is that the quarks themselves break free from their confinement entirely, dissolving the neutrons and protons into a sea of unbound quarks and gluons. This is quark matter, and its potential presence at the heart of neutron stars has been one of the most actively researched topics in theoretical astrophysics for decades. The idea that quark matter might exist inside neutron stars dates back to the early 1970s, shortly after the development of QCD as a theory. In 1965, Soviet physicists D.D. Ivanenko and D.F. Kurgelades first suggested that quark stars might exist, though at the time the idea was highly speculative. By the mid-1970s, as QCD matured and the concept of asymptotic freedom was established, the possibility of a deconfinement transition at high density became more concrete. Several groups of theorists began to construct models of neutron stars with quark matter cores, so-called hybrid stars, and to explore the observational consequences. The difficulty, then as now, is that the transition from hadronic matter to quark matter occurs in exactly the density range where neither nuclear theory nor perturbative QCD can make reliable predictions. This has led to a proliferation of models, each making different assumptions about the nature of the transition and the properties of the resulting quark matter. Some models assume a sharp, first-order phase transition, with a clear boundary between a hadronic outer core and a quark inner core. Others assume a smooth crossover, with matter gradually changing character over a range of densities. Still others assume a mixed phase, where hadronic matter and quark matter coexist in a complex, heterogeneous mixture, possibly with its own set of pasta-like structures at the hadron-quark interface. The diversity of models is both a strength and a weakness of the field. It is a strength because it reflects the genuine theoretical uncertainty and encourages a broad exploration of possibilities. It is a weakness because it makes it difficult to draw firm conclusions from observations. When you have dozens of models that all fit the data equally well, the data are not yet precise enough to discriminate between them, but the window is closing. With each new NICER measurement, each new gravitational wave detection, each new advance in lattice QCD or chiral effective field theory, the range of viable models narrows. The field is converging slowly but inexorably toward an answer. the liberation of quarks to understand what quark matter might be. You need to think about what happens to normal matter when it is subjected to pressures beyond anything found on Earth. Under ordinary conditions, quarks are confined inside hadrons. 3 quarks make a baryon, like a proton or neutron, or a quark and an antiquark make a meson. The quarks interact via the strong force, mediated by gluons, and the nature of this force keeps them permanently locked inside their parent particles. But theoretical calculations, backed by experimental evidence from particle colliders, show that under extreme conditions, this confinement can break down. There are 2 known ways to deconfine quarks. The first is to heat matter to extraordinary temperatures, above roughly 2 trillion degrees Kelvin. At these temperatures, the thermal energy of the particles is so great that the bonds between quarks are overwhelmed, and the quarks and gluons fly free. This is the quark-gluon plasma, a state of matter that existed everywhere in the universe for the first few microseconds after the Big Bang. It has been recreated, briefly, in laboratory experiments at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory in New York, and at the Large Hadron Collider at CERN in Switzerland, where gold or lead nuclei are smashed together at nearly the speed of light, producing tiny fireballs with temperatures exceeding 4 trillion degrees. The second way to deconfine quarks is not through heat, but through pressure. If you compress matter to densities several times greater than nuclear density, the hadrons are pushed so close together that their quarks begin to overlap. At some critical density, the distinction between this quark belongs to this neutron, and that quark belongs to that neutron, becomes meaningless. The quarks become deconfined, not because they have been given enough energy to escape their confinement, but because the confinement itself has been overwhelmed by the sheer density of the surrounding matter. The quarks are, in a sense, liberated not by force, but by crowding. This is the kind of quark matter that might exist in the cores of massive neutron stars, unlike the quark-gluon plasma produced in particle colliders, which is blazingly hot, but exists for only a tiny fraction of a second. The quark matter inside a neutron star would be relatively cold, by nuclear physics standards, anyway, still millions of degrees, but long-lived, persisting for billions of years, and the evidence that it actually exists is growing stronger. In 2020, a team of researchers, including Alexei Kirkella from CERN's Theory Department, published a groundbreaking paper in Nature Physics that combined theoretical calculations with astronomical observations to show that the most massive neutron stars likely contain cores filled with quark matter. Their approach was clever. They knew that at relatively low densities near the neutron star's crust, matter is well described by nuclear theory, specifically by a technique called chiral effective field theory. They also knew that at extremely high densities, far beyond what exists in any neutron star, matter is well described by perturbative QCD, the mathematical framework for quarks and gluons at high energy. The problem was the intermediate density regime, exactly where neutron star cores lie, where neither theory works well. So the team connected the 2 known endpoints, the low-density nuclear theory and the high-density quark theory, with a family of mathematical functions that smoothly interpolated between them. They then constrained these functions using 2 pieces of observational data. The fact that neutron stars can be as massive as 2 solar masses, and the tidal deformability measured from the G170,817 neutron star merger event. The result was striking. For neutron stars with masses around 1.4 solar masses, the equations of state agreed well with standard nuclear models, suggesting that these stars have purely hadronic cores. But for the most massive neutron stars, those approaching 2 solar masses, the data strongly favored the presence of quark matter cores. In fact, the team suggested that a 2 solar mass neutron star with a radius of about 12 kilometers could have a quark matter core with a radius of about 6.5 kilometers, roughly half the size of the entire star. A follow-up study published in Nature Communications in 2023 strengthened this conclusion using Bayesian statistical analysis and additional observational data. The probability that massive neutron stars contain quark matter cores was estimated at 80 to 90%. Not a certainty, but far from a long shot. If quark matter does exist in neutron star cores, it would represent the only place in the modern universe where this primordial state of matter persists. Everywhere else, the quark-gluon plasma that filled the early universe cooled and condensed into hadrons within the first microsecond of cosmic history. Only inside neutron stars, where gravity maintains the extreme density, could quark matter survive in perpetuity. But the story does not end with simple deconfined quarks. Because at the densities found in neutron star cores, the quark matter itself might undergo further transformations into even more exotic states. And one of the most remarkable of these involves a substance with a name that sounds like it belongs in a science fiction novel: strange matter. The quarks that make up ordinary protons and neutrons are limited to 2 types, or flavors: up quarks and down quarks. But the standard model of particle physics contains 6 flavors of quark in total: up, down, strange, charm, bottom, and top. The charm, bottom, and top quarks are far too heavy to be relevant at neutron star densities. But the strange quark, with a mass only modestly greater than the up and down quarks, could play a crucial role. Here is the key insight. In a dense sea of deconfined up and down quarks, the Pauli exclusion principle, the same quantum law that prevents 2 identical particles from occupying the same quantum state, creates enormous degeneracy pressure. The quarks fill up energy levels from the bottom, and the topmost occupied level, the Fermi surface, has a very high energy. But if strange quarks are introduced, they provide a new set of energy levels to fill. Some of the high-energy up and down quarks can convert into lower-energy strange quarks, reducing the overall energy of the system. In other words, a mixture of up, down, and strange quarks can be more stable than a mixture of just up and down quarks. This is the basis of the strange matter hypothesis, first proposed independently by Arnold Bodmer in 1971 and Edward Witten in 1984. In its most provocative form, the hypothesis suggests that strange quark matter, containing roughly equal numbers of up, down, and strange quarks, might be the true ground state of all matter. If this is correct, then ordinary nuclear matter, the protons and neutrons that make up everything around us, is not truly stable. It is merely metastable, preserved by an energy barrier that prevents it from spontaneously converting into strange matter. Much like a ball sitting in a shallow depression on a hillside, the ball could roll down to a lower energy state, but it needs a push to get over the lip of the depression. The implications of this hypothesis, if it were proven true, would be profound and somewhat unsettling. It would mean that all ordinary matter in the universe is, in principle, capable of converting into strange matter if given the right stimulus. A sufficiently energetic cosmic ray hitting a neutron star, for instance, might trigger the conversion. Theorists have even speculated about the existence of strangelids, tiny droplets of strange quark matter that might be produced in neutron star collisions and ejected into space. If a strangelet were to come into contact with ordinary matter, it could potentially catalyze its conversion into strange matter, growing like a snowball rolling downhill. This is the so-called strange matter catastrophe, and it has been invoked, albeit somewhat melodramatically, as a potential existential threat. In practice, the conditions required for such a conversion are extremely specific and unlikely, and the absence of any observed strangelet in cosmic ray data suggests that either strange matter is not the true ground state, or that the conversion process is prohibitively slow. But the very fact that this hypothesis cannot be definitively ruled out by current data speaks to the depth of our uncertainty about the behavior of matter at extreme densities. If the strange matter hypothesis is true, then the cores of the most massive neutron stars might not merely contain deconfined quarks. They might contain strange quark matter, a form of matter that is more stable than anything we know. And that was potentially the dominant form of matter in the first moments after the Big Bang. Some theorists have even speculated about the existence of entire stars made of strange matter, called strange stars, which would have properties subtly but measurably different from conventional neutron stars. The hypothesis remains unproven, and there is significant debate about whether the conditions inside neutron stars are really suitable for strange matter formation. But it is one of the more beautiful and unsettling ideas in modern physics. The possibility that the matter making up you, and the Earth, and the Sun, and every star in the sky is not the most stable arrangement of quarks in the universe. That somewhere, deep inside the hearts of dead stars, matter has found a lower, more fundamental state of being. Painting the void with color if quark matter exists inside neutron star cores, it almost certainly does not exist as a simple, featureless gas of free quarks. The same quantum mechanics that causes electrons to pair up in superconductors and neutrons to pair up in superfluids would cause quarks to pair up as well, creating a state of matter with properties that sound almost magical. The phenomenon is called color superconductivity, and it derives its name from the color charge of quarks. Just as electrically charged particles interact through the electromagnetic force, quarks carry a property called color charge that governs their interaction via the strong force. Despite the name, this has nothing to do with visible colors. It is simply a label, a way of distinguishing three types of strong force charge that quarks can carry, conventionally called red, green, and blue. Gluons, the particles that mediate the strong force, also carry color charge. And the theory that describes all of these interactions is quantum chromodynamics, literally the dynamics of color. In high-density quark matter, the quarks near the Fermi surface, the boundary between occupied and unoccupied energy states, experience an attractive interaction mediated by gluon exchange. This attraction causes quarks to form Cooper pairs, just as the phonon-mediated attraction between electrons causes Cooper pairing in conventional superconductors. But because quarks carry both color charge and flavor, up, down, strange, The possible pairing patterns are far more varied and complex than anything encountered in condensed matter physics. To understand why Cooper pairing is essentially inevitable in dense quark matter, consider the following argument. In any system of fermions, particles with half-integer spin, which includes quarks, at low temperature and high density, the particles fill up energy states from the bottom, creating a Fermi sea. The surface of this sea, the Fermi surface, is where all the interesting physics happens, because only particles near the Fermi surface have the freedom to change their state. Now, if there is any attractive interaction between particles at the Fermi surface, no matter how weak, it turns out that the system can lower its total energy by having those particles form pairs. This is the essence of the BCS theory of superconductivity, developed by John Bardeen, Leon Cooper, and Robert Schrieffer in 1957. And it applies to any Fermi system with attractive interactions. In metals, the attractive interaction is mediated by lattice vibrations called phonons, and the resulting Cooper pairs are electrons. In neutron star cores, the attractive interaction between neutrons produces neutron-Cooper pairs, yielding a superfluid. And in quark matter, the attractive one-gluon exchange interaction between quarks produces quark-Cooper pairs, yielding a color superconductor. The key difference between quark-Cooper pairs and electron-Cooper pairs is the richness of the internal quantum numbers. An electron has only one relevant quantum number for pairing: its spin, which can be up or down. A quark, by contrast, has three colors: red, green, blue, and three relevant flavors: up, down, strange, giving 9 possible species of quark. The number of possible pairing patterns among these 9 species is correspondingly vast, and different pairing patterns lead to different phases of color superconducting matter, each with its own distinctive properties. The simplest and most symmetric pairing pattern is called color flavor locking, or CFL. In the CFL phase, quarks of all 3 flavors, up, down, and strange, and all 3 colors, red, green, and blue, pair up in a maximally symmetric way. Each quark of a given color pairs with a quark of a different color and a different flavor, creating a condensate that simultaneously breaks the symmetry of color, charge, and flavor. The result is a state of matter with some truly remarkable properties. In the CFL phase, the color charge of the quarks is screened, similar to how the electric charge of electrons is screened in an ordinary superconductor. But because the quarks also have flavor, the screening also affects the flavor symmetry, creating a rich and complex pattern of symmetry breaking. The CFL phase is electrically neutral without the need for electrons, a striking property that distinguishes it from other phases of quark matter. It is also believed to be the ground state of quark matter at asymptotically high densities, meaning that if you compressed matter to truly extreme pressures, far beyond what exists in any neutron star, the CFL phase is what you would get at the intermediate densities that might actually exist inside neutron star cores. However, the situation is more complicated. The strange quark is heavier than the up and down quarks, which breaks the symmetry between the 3 flavors and can destabilize the CFL phase. Depending on the exact density, temperature, and strange quark mass, a variety of other pairing patterns might be favored instead. These include the 2-flavor color superconducting 2SC phase, in which only up and down quarks pair, while strange quarks remain unpaired, the gapless CFL phase, in which the pairing gaps for some quark species are reduced to zero, and a variety of even more exotic phases with names like the crystalline color, superconducting phase, and the color spin-locked phase. In December 2025, a team of researchers from TU Darmstadt and Goethe University Frankfurt published a paper in Physical Review Letters that provided the most detailed calculations, yet of color superconductivity under neutron star conditions. They computed next to leading order corrections to the pressure of quark matter in the CFL phase, incorporating the effects of the strange quark mass and the requirements of electric and color charge neutrality. Their key finding was that color superconductivity significantly increases the speed of sound in quark matter, which in turn increases the mechanical stiffness of the material. This stiffness could be crucial for explaining the stability of the most massive observed neutron stars, those approaching 2 solar masses. Without the additional pressure provided by color superconducting pairing, it might be difficult for quark matter to support such heavy stars against gravitational collapse. The researchers also placed constraints on the size of the pairing gap, the energy difference between the paired and unpaired states, finding that it must be less than about 140 million electron volts at the highest densities where their calculations are reliable. This is a significant constraint because many theoretical models had predicted larger gaps, and it suggests that color superconductivity, while likely present, may be a subtler effect than some had anticipated. Color superconductivity in neutron star cores, if confirmed, would represent a triumph of fundamental physics. It would connect the behavior of matter under the most extreme conditions in the universe to the same quantum mechanical principles that govern the mundane superconductors used in MRI machines and particle accelerators on Earth. It would show that the laws of physics, formulated in our modest terrestrial laboratories, extend unchanged to the hearts of dead stars. And it would add yet another entry to the already extraordinary list of phenomena occurring inside neutron stars: superfluidity, superconductivity, nuclear pasta, deconfined quarks, and now color superconductivity, all layered on top of each other in an object smaller than a major city. But proving that any of these exotic states actually exists is an enormous challenge. You cannot crack open a neutron star and examine its contents. You cannot recreate the conditions of a neutron star core in any laboratory on Earth. Instead, you must observe neutron stars from afar, using instruments of exquisite sensitivity, and infer the properties of their interiors from the signals they send across the void of space. And in recent years, those instruments have been delivering. Reading the stars from afar for most of the history of neutron star research, our understanding of these objects was limited by the bluntness of our tools. We could observe pulsars and measure their rotation periods and spin-down rates with great precision. We could detect X-ray emissions from neutron stars in binary systems. We could build theoretical models and compute equations of state. But we lacked the ability to precisely measure the two quantities that matter most for constraining the interior composition: the mass and the radius of a neutron star. Mass, at least, has been accessible for decades through observations of neutron stars in binary systems. By tracking the orbital dynamics of a neutron star and its companion, astronomers can use Kepler's laws and general relativistic corrections to determine the neutron star's mass with high precision. The most dramatic mass measurements have come from the technique of Shapiro delay, a relativistic effect in which the pulses from a pulsar are slightly delayed as they pass through the curved spacetime near a companion star. Using this method, astronomers have measured neutron star masses as high as about 2.1 solar masses for PSR J700 and 40 plus 6620. And the Black Widow pulsar PSR J900 and 52-607 has been estimated at a stunning 2.35 solar masses. Though with larger uncertainties, these mass measurements are crucial because they set a lower bound on the maximum mass that any viable equation of state must support. If your model predicts that neutron stars cannot exceed 1.8 solar masses, and we have observed one at 2.1 solar masses, your model is wrong. This simple constraint has already ruled out many theoretical equations of state, particularly those that include large quantities of hyperons or very soft quark matter. Radius measurements, however, have been much harder to obtain. A neutron star is tiny, about 20 kilometers across, and even the nearest ones are hundreds of light years away. Measuring the radius of such an object is like trying to determine the size of a bacterium sitting on the surface of the moon. You cannot simply take a photograph. This is where NASA's Neutron Star Interior Composition Explorer, known as NICER, has been transformative. NICER is an X-ray telescope mounted on the International Space Station, and it was specifically designed to measure neutron star radii with unprecedented precision. It does this by observing the X-ray emissions from hot spots on the surfaces of rapidly rotating pulsars. As the neutron star spins, these hot spots rotate in and out of view, producing regular variations in the X-ray brightness. But the neutron star's intense gravity bends the X-ray light, warping the apparent position and brightness of the hot spots in ways that depend on the star's mass and radius. By carefully modeling these relativistic effects and fitting them to the observed X-ray light curves, the NICER team can infer both the mass and radius of the neutron star. Since its launch in 2017, NICER has produced mass and radius measurements for several neutron stars. Among the most important results have been measurements of PSR J30 plus 451, a 1.4 solar mass neutron star found to have a radius of about 13 kilometers, and PSR J700 and 40 plus 6620, a much more massive star at about 2.1 solar masses with a radius of approximately 12.4 kilometers. Most recently, NICER measured the mass and radius of PSR J400 and 37-4715, the nearest and brightest millisecond pulsar, further tightening the constraints on the equation of state. The methodology behind these measurements is itself a marvel of modern physics. The hot spots on a neutron star's surface are not simple points of light. They have complex shapes, temperatures, and positions that evolve over time. The X-ray photons they emit are affected by the neutron star's extreme gravity, which bends their paths, alters their energies through gravitational redshift, and causes the apparent size and position of the hot spots to differ from their true sizes and positions. Modeling all of these effects requires sophisticated general relativistic rate tracing calculations, in which the paths of millions of individual photons are tracked through the curved spacetime around the neutron star. The resulting theoretical light curves are then compared to the observed data using Bayesian statistical methods, which provide probability distributions for the star's mass, radius, and other parameters. The computational demands are enormous. Each analysis of a single NICER target requires millions of CPU hours on high-performance computing clusters. The parameter space is high-dimensional, typically involving 15 or more parameters that describe the size, shape, location, and temperature of the hot spots, the mass and radius of the star, and the orientation of the star's rotation axis relative to Earth. Navigating this parameter space efficiently requires advanced sampling algorithms like Markov chain Monte Carlo and nested sampling. It is a testament to the ingenuity and perseverance of the NICER team that they have been able to extract such precise measurements from what is, fundamentally, a very subtle signal. These measurements have been genuinely surprising. The fact that the more massive star, J740, has a radius not dramatically smaller than the less massive star, J30, suggests that the equation of state of neutron star matter is relatively stiff at high densities. In other words, the matter in the core pushes back hard against gravity, preventing the star from compressing as much as some models predicted. This rules out the softest equations of state, including pure quark matter models without additional repulsive interactions, while favoring models that include either conventional nuclear matter with strong repulsive forces, hybrid models with a quark matter core surrounded by a hadronic mantle, or models incorporating exotic forms of matter like hyperons or color superconducting quarks. The other revolutionary tool for probing neutron star interiors is gravitational wave astronomy, which burst onto the scene with the detection of G170,817 on August 17, 2017. This event, detected by the LIGO and Virgo gravitational wave observatories, was produced by the collision and merger of two neutron stars in a galaxy called NGC 4993, about 140 million light-years from Earth. It was the first time gravitational waves had been detected from a neutron star merger. And unlike previous gravitational wave detections from black hole mergers, it was accompanied by a spectacular show of electromagnetic radiation observed by more than 70 telescopes around the world and in space. The gravitational wave signal from G170,817 contained a treasure trove of information about neutron star interiors. As the two neutron stars spiraled toward each other in the final moments before collision, each one was slightly deformed by the tidal gravitational pull of its companion. The degree of this deformation, known as the tidal deformability, depends directly on the equation of state. A stiffer equation of state makes the star more resistant to deformation, while a softer one makes it squishier. By measuring the tidal deformability from the gravitational wave signal, the LIGO Virgo team was able to constrain the equation of state independently of any X-ray observations. Think of it this way. Imagine holding a ball of clay and a ball of steel, each the same size and weight. If you squeeze the clay ball, it deforms easily. If you squeeze the steel ball, it barely changes shape. The degree of deformation tells you something about what the ball is made of, about the internal forces that hold it together. In a neutron star merger, gravity does the squeezing, and the gravitational waves carry away the answer. The LIGO Virgo team found that the neutron stars in G100 and 70,817 were neither extremely squishy nor extremely rigid, ruling out equations of state at both extremes. The result was beautifully complementary to NICER's measurements. Together, the two data sets dramatically narrowed the range of allowed equations of state, ruling out both the stiffest and the softest extremes, and pointing toward a middle ground that is consistent with, though does not definitively prove, the presence of exotic matter in the most massive neutron star cores. The event of August 17, 2017, was extraordinary not just for the gravitational wave detection, but for the electromagnetic follow-up. Within seconds of the merger, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst, confirming a decades-old hypothesis that such bursts are produced by neutron star mergers. Within hours, ground-based telescopes around the world had identified the optical counterpart, a transient source of light in the galaxy NGC 4993 that quickly reddened and faded over the following days and weeks. This was the kilonova. But G100 and 70,817 gave us more than just equation of state constraints. The electromagnetic counterpart of the event, the kilonova, provided direct evidence that neutron star mergers are cosmic factories for the heaviest elements in the periodic table. The optical and infrared emissions from the kilonova were powered by the radioactive decay of newly synthesized heavy elements, created through a process called rapid neutron capture, or the ARP process. Analysis of the light suggested that the merger produced about 16,000 Earth masses of heavy elements, including roughly 10 Earth masses of gold and platinum alone. This means that every gold ring, every platinum wedding band, every trace of iodine in your thyroid gland was likely forged in the collision of neutron stars billions of years ago. The exotic material locked inside these dead stars, material that once existed in the most extreme conditions imaginable, was violently ejected into space and eventually incorporated into the gas clouds that formed our solar system, our planet, and ultimately us. Looking ahead, the next generation of gravitational wave observatories, including the planned Einstein Telescope in Europe and Cosmic Explorer in the United States, will be sensitive enough to detect hundreds or even thousands of neutron star mergers per year, each one providing new data on tidal deformabilities, merger dynamics, and post-merger remnants, combined with continued observations from NICER and future X-ray missions. These data will progressively tighten the constraints on the equation of state, and perhaps within the next decade or two, definitively resolve the question of what lies at the heart of a neutron star. The Einstein Telescope, planned for construction in Europe in the early 2030s, will be a triangular underground detector with arms 10 kilometers long, roughly 2.5 times longer than the current LIGO detectors. It will be sensitive to gravitational wave frequencies from about 2 Hz to 10,000 Hz, a range that encompasses not only the in-spiral and merger of neutron stars, but also the post-merger oscillations of the remnant. These post-merger signals, which current detectors cannot reach, encode direct information about the behavior of matter at densities exceeding nuclear density. If the equation of state undergoes a phase transition from hadronic to quark matter, the post-merger signal would show characteristic changes in frequency that would be a smoking gun for the presence of exotic matter. Cosmic Explorer, a proposed US-based detector with arms 40 kilometers long, would push the sensitivity even further, allowing the detection of neutron star mergers all the way out to the edge of the observable universe. At that range, the number of detectable events would be enormous, potentially thousands per year, providing a statistical picture of neutron star properties that would leave very little room for ambiguity. The heavy ion physics community is contributing as well. Experiments at facilities like the Relativistic Heavy Ion Collider at Brookhaven and the Large Hadron Collider at CERN continue to study the quark-gluon plasma, providing data on the properties of deconfined quark matter at high temperatures. Meanwhile, the Facility for Rare Isotope Beams, or FRIB, at Michigan State University, which began operations in 2022, is producing exotic, neutron-rich nuclei that exist nowhere in nature, helping physicists test the nuclear forces that govern the behavior of matter in neutron star crusts and outer cores, and lattice QCD calculations, a technique for numerically simulating QCD on a discrete grid of spacetime points, are steadily improving in their ability to model quark matter at the finite densities relevant to neutron star interiors. A 2025 paper in Physical Review Letters by the NPL-QCD collaboration used lattice QCD to constrain the equation of state of dense nuclear matter for the first time from first principles, a milestone that could open new avenues for understanding the neutron star interior, the question that endures. And so we arrive at the end of our journey, or rather at the edge of our knowledge, which in the case of neutron star interiors amounts to the same thing. We know with considerable confidence what the outer layers of a neutron star look like. We understand the atmosphere, the ocean, the crystalline outer crust with its progressively more neutron-rich nuclei. We have strong theoretical reasons, supported by indirect observational evidence, to believe that the inner crust contains nuclear pasta, that extraordinary assemblage of exotic structures that represents the strongest material in the known universe. We know that the outer core is a superfluid, superconducting sea of neutrons, protons, electrons, and muons, a medium where matter flows without friction and electrical currents persist without resistance at temperatures of hundreds of millions of degrees. But the inner core, the heart of the neutron star, remains hidden. We have candidates. We have hypotheses. We have models that predict quark matter, strange matter, hyperonic matter, color superconducting matter, Bose-Einstein condensates of mesons, and more. Some of these models agree with current observations. Some are in tension with them. None have been definitively confirmed or ruled out. The data from NICER and LIGO have narrowed the field considerably, pushing us toward equations of state that are moderately stiff, and that may include a phase transition from hadronic to quark matter at densities above about twice nuclear density. The probability that the most massive neutron stars contain quark matter cores has been estimated at 80 to 90% by several independent analyses. But a probability, even a high one, is not a proof. What would it take to settle the question? One possibility is the detection of a strong phase transition in a neutron star, a sharp boundary between hadronic matter in the outer core and quark matter in the inner core. Such a transition would leave a distinctive signature in the mass-radius relationship of neutron stars, producing a branch or kink in the curve that would be visible in sufficiently precise measurements. Current data are not quite precise enough to detect this, but future observations from NICER and next-generation X-ray missions could potentially resolve it. Another possibility is the detection of gravitational waves from a neutron star merger that exhibits a post-merger signal. The brief, chaotic gravitational wave emission produced by the remnant in the moments after the collision. The frequency and evolution of this post-merger signal are extremely sensitive to the equation of state and could reveal the presence of quark matter in a way that no other observation could. Current gravitational wave detectors are not sensitive enough in the relevant frequency range, a few kilohertz, to detect post-merger signals from typical events. But the next generation of detectors should be. A third possibility, more speculative but deeply exciting, is the discovery of a quark star, a compact object composed entirely of quark matter from its core to its surface. Such an object, if it exists, would have properties measurably different from a conventional neutron star, including a different mass-radius relationship and a different cooling curve. The detection of even a single quark star would immediately resolve multiple open questions about the behavior of matter at extreme densities. And there is always the possibility that the answer will come from a direction nobody expects. Science has a habit of doing that. What we can say with certainty is that neutron stars represent one of nature's most extraordinary gifts to physicists. They are laboratories that we could never build, furnaces we could never ignite, pressure chambers we could never seal. They take the same quarks and electrons that make up your body and mine and subject them to conditions that push matter to its absolute limits. And somewhere inside those limits, hidden behind layers of iron and pasta and superfluid, and perhaps something stranger still, the universe is keeping one of its most profound secrets. We are closer to uncovering it than we have ever been. But we are not there yet. The core of a neutron star remains, for now, the most inaccessible and mysterious few cubic kilometers in the observable universe. It is a place where the known laws of physics blur and blend, where the particles that build our world may lose their identities and merge into something new. It is a place where the universe is still, after 14 billion years, experimenting with what matter can be. There is something deeply humbling about that. We have mapped the cosmic microwave background radiation from when the universe was 380,000 years old. We have detected gravitational waves from black hole collisions 1 billion light years away. We have sent spacecraft to the edge of the solar system and robots to the surface of Mars, but a ball of matter 20 kilometers across, smaller than the metro area of most major cities, remains opaque to our understanding. The core of a neutron star is as close to an alien world as exists in nature, a place where the physics that governs every atom of your body and every star in the sky is stretched to its absolute limit, and where the answers to some of the deepest questions about the nature of matter itself are written in a language we have not yet fully learned to read. What we have learned, though, is extraordinary. We have learned that matter, the same matter that makes up mountains and oceans and human beings, can exist in states so extreme that they border on the surreal. We have learned that the remnants of dead stars contain superfluids at hundreds of millions of degrees, magnetic fields that warp the vacuum of space, and structures made of nuclear material named after pasta. We have learned that the quarks inside your protons and neutrons, the very building blocks of everything you have ever touched, may be able to escape their confinement and flow freely like a liquid under the right conditions. Conditions that may exist at this very moment inside hundreds of millions of neutron stars scattered throughout our galaxy. We have learned that the gold in your ring and the platinum in your phone were forged in the collision of these neutron stars. Their exotic interiors violently ejected into space and scattered across the cosmos to become the raw material for planets and people. And perhaps most remarkably of all, we have learned how to ask these questions in the first place. The equation of state of dense matter, the mass-radius relationship of neutron stars, the tidal deformability of merging compact objects. These are not easy concepts. They require the full machinery of general relativity, quantum chromodynamics, nuclear physics, and statistical inference. Brought together and focused on an object, we cannot visit, cannot sample, and cannot reproduce. The fact that we can say anything meaningful about what lies at the center of a neutron star, let alone place probabilistic constraints on whether it contains quark matter, is a testament to the power of human curiosity and the ingenuity of the methods we have developed to satisfy it. And we, from our fragile blue planet, are watching, listening, measuring, slowly, painstakingly, inch by inch, pulling back the veil. One day, we will know what is hidden in the core of a neutron star, and when we do, it will change everything we thought we understood about the stuff the universe is made of. Until then, we keep looking up. If you enjoyed this exploration of one of the deepest mysteries in modern physics, please take a moment to hit that like button and subscribe to the channel. Leave a comment and let us know what you think might be hiding at the center of a neutron star. Thanks for watching, and we will see you next time.